Good evening, everyone. Thank you for joining us tonight for our Caltech Astronomy Stargazing Lecture. I'm Dr. Cameron Hummels. I'm a research scientist here who organizes these events, and I will be your host for tonight's activities. I have a few brief announcements before we get started, but let me lay out the schedule for tonight. In a few moments, I'll introduce our speaker, who's going to talk all about do electrons spin, but more importantly, how our interpretation of different physical theories reflects how the actual world exists on, in this case, very small scales. And then following the presentation, that'll go about 30 minutes, plus or minus. And then we'll have a brief Q&A where we take questions from you guys. And then we'll have a brief intermission. And that's when the choose your own adventure portion of the evening begins. You can stick around in the auditorium for the following hour or so, and we'll have a Q&A panel consisting of our speaker and two of his colleagues in the philosophy of science department here, who specialize in areas of science and what our philosophy and understanding of those things means about the real world. So at the same time as our panel Q&A is going on in here, we'll have telescopes outside on the adjacent athletic fields just behind me here that you can go look through. So it's clear weather tonight. We've got a few telescopes set up. There's a beautiful first quarter moon visible in the sky, and the moon's always a showstopper to look at. There's actually a lunar eclipse happening next week, next Thursday night. We might have an event for it. I don't know. We'll see. I need to figure out if we're going to do something for it. But there's the first quarter moon to look at. You can see various craters and so on and so forth, as well as we'll have two additional telescopes, smart telescopes that are able to see deeper objects in the sky, fainter objects in the sky. Some of the targets might be the Whirlpool Galaxy, the Hercules Cluster, or the Dumbbell Nebula, this planetary nebula of gas surrounding a star that recently kind of died. It's morbid, but it's a really cool thing to see through the telescope. And that will continue at the same time as we're doing the panel. So feel free, stick around for a bit, ask questions about the philosophy of science and science in general to our panel, then maybe go check out the telescopes or vice versa. And the whole event will close by 10 o'clock or so tonight. These events take place once a month on Friday nights, like tonight. Our next one, I forget the exact date, I think it's September 18th. And our speaker is Dr. Amy Hoffman from the Planetary Science Department, who I don't know what she's going to talk about. Probably Venus. She's involved in a mission that's going to Venus. So we might hear all about the state of the art with respect to one of our nearest planetary neighbors. But stay tuned. I'll put out the announcement for that in the next week or two. In addition to these events that we host here, we have a sister series of events called the Astronomy on Tap events that take place at a bar in Old Town, Pasadena, just a few miles drive from here. It's called the Doghouse Beer Garden. And despite being a bar and an outdoor tavern, it is open to all ages, so families are welcome. I recognize some faces in the audience as people, in fact, an Astronomy on Tap t-shirt right here. So if you haven't come, it's super fun. It's all ages. It's less formal than this because it's in a bar restaurant, but we have telescopes. We have two 15-minute public level presentations on different aspects of astronomy or space science. And then we have astronomy themed pub trivia. So it ends up being a really nice time. Our next one of those will be a week and a half from now on Monday, August 31st, a week from this coming Monday. And the two presentations will be given all about telescopes. One presentation will be about ground-based telescopes, like the ones that we're going to use tonight, but more professional grade, much larger telescopes that are used for research, like the Keck telescopes or the Very Large Telescope, or the telescope that's being built right now, the Extremely Large Telescope in Chile. And then the other presentation is going to be all about space-based telescopes, and both past space-based telescopes and present, like the Hubble Space Telescope or the James Webb Space Telescope, or the Roman Space Telescope that's launching in 9 days from now. Very exciting. We had a presentation about that a couple of months ago, but also future designs for telescopes in space, not just visible wavelengths of telescopes, but radio waves and gravitational waves and X-rays and what we can really learn about the universe from this vast array of different instruments that we build to try and perceive the world around us. So it should be quite exciting. Other announcements. Next month, there will be 2 national parks that are hosting dark sky festivals that we'll be contributing to. Unfortunately, they're the same weekend, so it's very difficult to attend both at the same time. I wish I could, but they're probably a 5-6 hour drive between the two. One will be at Sequoia National Park, just a few hours north of here in the Sierra Mountains, big trees. And that will be September 11th through the 13th, Friday through Sunday. And we'll feature all manner of telescopes in the evenings, star parties that are open to everyone, and you can go look through dozens of telescopes, as well as public level presentations throughout the day, science demonstrations, these sorts of activities. As I said, it's open, it's free. You just have to get entrance to the park, but if you have a parks pass, that's free. If you have to pay, I don't remember what the fee is for just going in for a single visit. But we'll have 8 graduate students and postdocs who are going up to Sequoia to give presentations and help with the telescopes. And the same weekend, another group of us that I'll actually be at is at Great Basin National Park, which is about a 7-hour, 8-hour drive from here. It's in eastern Nevada, and it's actually amongst the darkest sky national parks in the United States because it's so remote. The closest cities are Las Vegas and Salt Lake City, which are each about a 4-hour drive away. And so it's really in the middle of nowhere. And so because of that, you don't have a lot of light pollution that affects the surface brightness of the sky. And so you're very able to see the dark objects when it gets dark. You can see distant objects throughout our solar system and beyond. You can see the Milky Way naked eye. It's wonderful. And like the Sequoia event, there will be a number of different presentations. We're going to run an astronomy on tap there at the national park, and we'll give presentations and telescopes and the like. So if you're interested in either of those things, I realize it's a bit of a drive, but in order to escape the light polluted skies of LA County, you have to get away. And those are 2 wonderful places to go. So I encourage people to check it out if they're interested. I think those are my announcements for now. So I'll introduce our speaker. Our speaker is a little bit unique relative to the decade or so that we've had these presentations. So typically when we have speakers, they're talking about astronomy related results or a new telescope that's come out or a new discovery that was made with astronomy and telescopes. But this speaker comes from the branch of physics that involves philosophy. So he studied both philosophy as well as physics at MIT as an undergraduate student, before then doing a philosophy of physics master's program at Oxford in the UK, and then coming back to the US and receiving a master's in physics as well as a PhD in philosophy from University of Michigan. Following that, he came to Caltech as a postdoc in philosophy of science. He was here for a few years before he became a professor at UC San Diego. And then he came back almost a decade ago, he came back to Caltech, and he's now a professor in the humanities department here studying the philosophy of science and specifically the philosophy of physics. His specialties are primarily in the field of quantum mechanics, quantum field theory, and classical field theory. And when I say that, he's a philosopher. I mean, he's both a trained physicist, but he's a philosopher who works to understand and interpret these models like quantum mechanics that are extremely accurate and effective for us to being able to predict the future. But what does it mean for reality itself? What does it mean on these scales? And I think that's a really important question that a lot of us, at least in the sciences, think about, but don't think as deeply about this as he and his colleagues do. So please welcome our speaker tonight, Professor Chip Sebens.
Thank you so much. It's an honor to speak to all of you and to have such a packed house tonight. This is wonderful. As you heard in the introduction there, I work at the border between philosophy and physics. I'm a philosopher, but I study physics. In the talk tonight, it might seem like I'm giving a physics talk, but the way that philosophers look at physics is a bit different. Physicists can be, in a way, very practical. They are trying to develop equations that make accurate predictions, and they play with the equations and try new ones to figure out how to do that. But they're not always asking how those equations should be interpreted, what they say about the world around us, which equations are fundamental to the theory. philosophers are famously impractical. And there's a famous joke about philosophers that philosophers wonder whether what works in practice will work in theory. And you'll see that kind of spirit alive today in the talk tonight, where I'm going to be looking at these theories of physics and asking how they should be understood, what they really say, can they be made coherent and consistent and precise in certain ways that philosophers really care about. Philosophers of physics ask all sorts of different questions, but the questions that I find myself asking the most for many different theories in physics is, how should we formulate this theory so that it's clear about what exists, what philosophers call the ontology, and what are the laws of nature according to this theory? So what is the stuff, and what rules govern that stuff? What rules govern the evolution of those things? In practice, that's very technical work. It looks a lot like theoretical physics. But today I'm going to try to keep it simple and accessible and to focus on the visuals. Okay. So you can imagine that this project of trying to articulate the laws of nature and the ontology, what exists, is going to be pretty tricky for certain theories in physics. Quantum mechanics is notoriously hard to understand. It's a strange theory. So if you're trying to figure out the laws and ontology of quantum mechanics, that's going to be tough. If you're thinking about what's going on inside an atom, we know that the center of the atom, the nucleus, has protons and neutrons, and there are electrons whizzing about the nucleus. Well, that simple model where you have some sort of point electron or very small electrons going around the nucleus, that's not ultimately right. Somehow we have to replace those classical particles with quantum particles described by a quantum wave function. So you get a picture more like this of the atom. But what exactly is that wave function is something that philosophers are quite concerned with. They say that the wave function gives probabilities for finding a particle different places, but what is it telling you about what's actually happening at a moment? There are lots of questions about what's going on with the wave function. Sometimes you have wave functions evolving and doing things. So the picture on the right shows a wave passing through two slits and approaching a screen. And in that time, it obeys a wave equation. That's your law of nature that it's obeying, the Schrodinger equation. But when it hits the screen, you see a single dot. That's what's shown on the lower right there. Each time you run this experiment, you get one dot. And if you run the experiment over and over again, you get lots of dots that show these stripes, this interference pattern. What are the laws of nature there? It seems like there's one set of laws when the particle is acting like a wave as it's approaching the screen, but then when it hits the screen, the laws look different. All of a sudden you get a single dot instead of an image of the wave. So can we articulate clear laws for quantum mechanics? Does the particle behave differently when you're looking at it, when you make an observation at the end of this experiment? Developing that idea that things might behave differently when you're looking at them, you get weird paradoxes like Schrodinger's cat. So, things are clearly going to be tough when it comes to quantum mechanics, trying to articulate the laws of ontology. You get a variety of different proposals called interpretations of quantum mechanics. And I teach a whole course on those, and I find that very interesting. But I thought today we should start with an easier case, start with classical electromagnetism. So, we can think about electric effects like opposite charges attracting, magnetic effects like the little magnets in these compasses interacting with the bar magnet here. Okay, so we have a very good theory of classical electromagnetism. It's taught in high school, it's taught in college. It seems fairly cut and dried. You might think this is a theory of physics where specifying the laws of ontology shouldn't be so hard. But there actually are some very difficult questions about how classical electromagnetism should be formulated. One of the questions is, what's going on here with these compasses? Why are they aligning themselves in this way? Is there a magnetic field around the bar magnet and they're showing you the direction in which the magnetic field is pointing? They're responding to the magnetic field at their location? Or are they directly interacting with the bar magnet across a gap in space? Is this a kind of action at a distance theory? So is the magnetic field a real thing or not? Is it a theory of direct interaction between bodies? We can ask the same question about the electric field. If you have a negative charge, there's an electric field that's always pointing in towards that negative charge. We use that electric field to calculate how other bodies would move in the presence of this negative charge. But is that electric field really there? Okay, now you're starting to see a kind of philosophical question about physics. Are these fields real or not? How would you answer that? How would you figure out if the field is real or not? If you predict the same motion for bodies that come near this negative charge, how would you know if there actually is an electric field or whether they're just interacting directly with the negative charge? Here's one way you can try to answer that question, is to think about conservation of energy and momentum. That's a very central principle in physics. We think energy and momentum should be conserved. Well, if electric and magnetic fields are real, we have a good story to tell about energy and momentum conservation, and if they're not real, we don't. So it seems like a good reason to treat them as real. Let me explain. If you imagine accelerating a charged body and then having it move at constant velocity, which is shown here, that requires a certain amount of energy to be imparted to accelerate that body and get it moving at a constant velocity. It's actually harder to accelerate a charged body than it is to accelerate an uncharged body. So if a body has positive charge or negative charge, it's harder to push it and get it going at a constant velocity than if it has no charge. That's a small effect for large bodies, but it would get larger as the body gets smaller and smaller. Okay, where does that additional energy go? It takes more energy to accelerate the charged body than an uncharged body. What happens to that energy? It's not in the kinetic energy of the body itself. The body's moving with the same velocity, whether it's charged or uncharged. If the electromagnetic fields are real, we can say, oh, some of that energy went into this wave that propagates out from the body. That wave in the electromagnetic field itself carries energy. You have to put in extra energy to accelerate the body because you're not just giving that body kinetic energy, you're also making that wave, and the wave carries away energy. So if the fields are real, we get conservation of energy and momentum. We have to attribute the fields an energy density. The energy density for the electromagnetic field is proportional to the square of the electric field plus the square of the magnetic field. And a momentum density, which is proportional to the cross product of the electric and magnetic field. So for our negative charge, there's an energy density in the electric field. It gets stronger, higher energy density as you get closer to the body where the electric field is stronger. And there's no momentum density here. It's just a body at rest, and there's no momentum in the field. If you think about an electromagnetic wave, the electromagnetic wave has regions of high energy density and regions of low energy density. And if you take E cross B using the right-hand rule, the cross product of the electric field and the magnetic field, you get a momentum density for the electromagnetic field, and the momentum density points in the direction that the wave is going, which makes sense. Okay, so we can treat electric and magnetic fields as real things that possess these properties of energy and momentum. There's another question that we can ask about the ontology of classical electromagnetism. There's not only fields, there's also charged matter. What kind of thing is charged matter? Often in elementary problems in electromagnetism, you treat the charged matter as point charges. You ignore the size and pretend like it's just a mass and a charge located at a point. Could the theory be formulated that way at the fundamental level? Could you think ultimately this is a theory of point charges interacting with each other? Well, it runs into problems. If you try to calculate the force between two negatively charged point charges, you might do that by looking at the electric field produced by the red charge and seeing what force that electric field would exert on the blue charge. But that would be missing something. You'd be neglecting the contribution that the blue charge itself makes to the electric field. When you include that, the total electric field looks like this. And if you look at the electric field at the location of the blue point charge to figure out the force on the blue point charge, it's ill-defined. As you get closer and closer to the electric field, to the blue charge in different directions, your electric field is pointing in different directions. And the electric field becomes stronger and stronger as you get towards the blue point charge. So we can't actually use the total electric field to calculate the force on the blue point charge. So there's a kind of self-force problem that arises from for point charges. There's also a problem with radiation reaction for point charges. I mentioned already how it's harder to accelerate a charged body than an uncharged body. This wave propagates outwards. If that body has some size, it's not just a point charge, maybe you think of it as a charged sphere or something like that, we can imagine that as that wave propagates through the body, it exerts force on the body. As it propagates through the body on its way out, it exerts force. So if it's a negatively charged body, the electric field might look like this. As that wave is passing through the body, the electric field points in the direction of motion, but the body is negatively charged, so it experiences a force opposing its motion, a force that makes it harder to accelerate than it otherwise would be. That makes sense. If it has size, we can explain why it's harder to accelerate using this radiation reaction force. If it does not have size, if it's a point charge, we run into problems here. How do we make sense of this radiation reaction force? It's troublesome. And then final problem for point charges is that the self-energy blows up. So the electric field gets stronger and stronger as you approach a point charge. And I said before that the energy density in the electric field is proportional to the square of the electric field. When you integrate that over all of space, when you sum all of that energy density, how much energy is there for a point charge? It's infinite, an infinite amount of energy, because it gets so strong as you get close to the point charge. So there's a problem of infinite self-energy for point charges. On the other hand, if you have like a cloud of charge, then as you get close to that cloud from far away, the electric field gets stronger. But as you go towards the center of the cloud, it actually gets weaker. And at the very center of the cloud, it's zero. When you integrate that and find the total energy in the electric field for a cloud of charge, it's finite. It's not infinite. Things are well behaved. Or you could do the same calculation for a sphere of charge or something like that. Charge distributions are okay. Point charges lead to problems of self-energy. So there's a bunch of reasons why I don't like point charges. I think classical electromagnetism is best understood as a theory where the electric and magnetic fields are real and where there are not actually any point charges. You might use them as an idealization or an approximation for certain purposes, but they're not part of the fundamental formulation of the theory. All right, now's a good time to step back and give the outline of the talk, which we've gone through some of already. So I began talking about laws of ontology, things that philosophers are trying to get clear on. The question of whether electric and magnetic fields are real, and some problems that point charges run into in classical electromagnetism. Staying in classical electromagnetism, next we're going to talk about spinning charged bodies and how they behave. Then we'll move to electrons and asking how electron spin should be understood. A couple different options, a couple different ideas about what's going on with electron spin. Then we'll see a couple problems for the idea that electrons really spin. We'll talk briefly about quantum field theory and two different ways of approaching quantum field theory, of formulating the theory, a particle approach and a field approach. And then we're going to come back to what's going on inside the atom. All right. So if you have a spinning charged body, just in a regular classical theory of electromagnetism, that spinning charged body has angular momentum because the mass is rotating about a central axis. And it's also going to act like a magnet. When you work through the equations of classical electromagnetism through Maxwell's equations, you can figure out how moving charges source magnetic fields. And in this case, a rotating charge gives rise to this magnetic field that looks very much like the magnetic field of a bar magnet. Same kind of magnetic field. So a spinning charge body acts like a magnet. Maybe this is familiar from the idea that a solenoid has charges going around a wire in loops, this rotating charge, and then acts like a magnet. Okay, so a spinning charge body has angular momentum, acts like a magnet. Electrons are similar. Electrons have angular momentum, and they act like magnets. So we say that they have a property called spin. That's the way it's normally described in quantum mechanics textbooks. So electrons have a property called spin. Whether electrons really spin, that's a matter of debate. That's what we're going to be talking about later, but they have this property called spin. Okay, how do we know that they act like a magnet, or in what way do they act like a magnet? In one way they act like a magnet is when you get a bunch of electrons together, like you have a bunch of atoms together in some solid. If the electrons have their spins unaligned, like randomly oriented, the total big object does not act like a magnet. But if those spins are aligned, it acts like a magnet. Indeed, the bar magnet that we were just talking about, this is what's happening inside a bar magnet. The reason why the bar magnet itself acts like a magnet is because there are so many electron spins that are aligned together. And when you have a lot of electrons with their spins aligned together, you get not just a small magnet, but a big magnet. And that's quite interesting because then this question about whether electrons are really rotating, it's a question about where the sort of magnetic properties of electrons come from. Does it come from true rotation or not? But it's also a question about where the magnetic properties of bar magnets come from. Are bar magnets somehow like built from fundamental tiny magnets, or are they built from spinning things? Is it a rotation of charge that gives rise to the magnetic fields around bar magnets? So there's a kind of deep question here about whether magnetic fields are always sourced by moving charges. Is it always the motion of charge that gives rise to magnetic fields? Or can magnetic fields sometimes arise from other things where it's not the motion of charge, some kind of intrinsic or basic magnets? All right, so the textbook line on electron spin is here from a popular textbook by Griffiths and Schroeder. The electron, as far as we know, is a structureless point particle, and its spin angular momentum cannot be decomposed into orbital angular momentum of constituent parts. This angular momentum it has associated with this property called spin cannot be reduced to some parts of the electron orbiting around some central axis. That's what Griffiths is claiming here in Schroeder. Okay, so the story here is that the electron has a property called spin, but it does not really spin. The electron has an intrinsic angular momentum and an intrinsic magnetic moment. Magnetic moment being a word for magnetic strength, how strong of a magnet it acts like. So he's calling it a structureless point particle. If it's just a point particle, there's nothing to be really spinning around a central axis, it's just a point. So if it's going to have angular momentum and it's going to have magnetic moment, they're intrinsic, they belong to it itself, they're not the result of actual rotation. And that leads to a kind of strange picture of reality in my mind, because it means of all the angular momentum we have out there, some of it has to do with rotation around some axis, and some of it is just intrinsic, it's just basic. And sometimes magnetic fields result from the motion of charge, and sometimes magnetic fields result from these intrinsic magnetic moments. So it's kind of a disunified picture of nature that I find a bit unattractive. It would be nice if angular momentum always came from rotation, and magnetic fields always came from the motion of charge. Okay, good. Now, they put forward this picture that the electron is a structureless point particle. Of course, they don't think it's a classical point particle. This is a book on quantum mechanics, so they think in some sense it's a quantum point particle. That's the picture they have. But they do lead the reader to another option. They have a footnote citing an alternative interpretation of what's going on here, a footnote citing Hans Ohanian's article, What is Spin? They say you can look there for a contrary interpretation. So what is this contrary interpretation, and could it be right? Okay, so in the abstract to Ohanian's article, What is Spin? He writes, it can be shown that the spin may be regarded as an angular momentum generated by a circulating flow of energy in the wave field of the electron. Likewise, the magnetic moment may be regarded as generated by a circulating flow of charge in the wave field. Okay, so that's a very different picture. It's not a point particle with intrinsic angular momentum and magnetic moment. The angular momentum results from a rotation of energy. If you're thinking, wait, why is it energy and not mass? Remember E equals mc squared, mass energy equivalence. So if there's a rotation of energy, in some sense that's like a rotation of mass. Likewise, the magnetic moment may be regarded as generated by a circulating flow of charge in the wave field. This is a field representation of the electron that has charge, and the charge is rotating. Okay, so we can sketch now two ideas of what an electron is and how we should understand electron spin. So the first option, the electron is modeled classically, not doing quantum physics yet, as a point charge. It has intrinsic angular momentum and intrinsic magnetic moment. It's not actually rotating. The quantum electron is in a superposition of these classical states, described by some kind of wave function. Okay. You can tell already, I've given you a number of reasons why I'm not going to like option one. Point charges, I think, don't work very well in classical electromagnetism. Intrinsic angular momentum and intrinsic magnetic moment paints a kind of disunified picture of the world. But that's one option, option one. Option two, kind of building on the ideas in Ohanian's paper, the electron can be modeled classically as a lump of energy and charge in the Dirac field. The Dirac field is to electrons as the electromagnetic field is to photons. You might kind of think of it that way. So the Dirac field is the kind of field that you associate with the electron, just like the electromagnetic field is the field you associate with the photon. Okay, so we're thinking classically, the electron is this kind of cloud, this kind of lump of energy and charge in the Dirac field. The classical representation of the electron is not as a point particle, but as a spread out kind of thing. In that lump of energy and charge, does the lump of energy and charge just stay still, or does it move? It moves. It circles around a central axis. So we have the angular momentum and magnetic moment of the electron resulting from the rotation of energy and charge in this classical picture. The classical picture is not the final picture here. The classical picture is a kind of warm-up. Ultimately, we want a quantum description of the electron. And the quantum electron is in a superposition of these classical states. So on the second option, the classical states that are being superposed are not classical states of a point particle with intrinsic angular momentum and magnetic moment. The classical states that are being superposed are field states, states of a spread out cloud kind of electron. The picture of the electron that you have here classically, the picture of the electron as a lump in the Dirac field looks something like this. There's a cloud of charge. Here I show the current density with these arrows rotating around a central axis. I mentioned before that the electromagnetic field has energy density and momentum density. The Dirac field, the field for the electron, also has energy density and momentum density. The electromagnetic field does not itself carry charge. The electromagnetic field is charge neutral because photons don't have charge. So that field doesn't have charge density or current density, where current density is associated with the flow of charge, but the Dirac field does. The Dirac field has charge density and current density. So it has all these properties: energy density, momentum density, charge density, current density. And on the second option from the slide before, we let this classical field enter superpositions of different states. So here are the two options about what an electron is. They both involve a famous equation called the Dirac equation, but they use the Dirac equation in different ways. In option one, the Dirac equation is interpreted as the quantum equation for the point particle electron, and the psi that appears in the Dirac equation is a wave function for the electron. In option two, the Dirac equation is used as well, but now the Dirac equation is interpreted as part of classical field theory. So the Dirac equation gives the classical field dynamics, how the classical field evolves for the classical Dirac field represented by psi. So same math, but different interpretation. We see here, these kind of philosophical or foundational moves when you're debating how to interpret the physics. Yes, the Dirac equation works well, but what place should it ultimately have in our theorizing? Is the Dirac equation an equation as to how a quantum wave function for the electron evolves? Or is it better to at least sometimes think of the Dirac equation as an equation for how a classical field evolves? All right. So a couple of problems for the idea that the electron spins. A couple of the reasons why it's not everyone thinks of the electron as truly spinning. First, you can look at the ratio of the electron's angular momentum to its magnetic moment. This is called the gyromagnetic ratio. And it's not what you would expect for a classical spinning body. It's off by a factor of approximately 2. So if you have a spinning body that has mass and it has charge, and it's symmetric about some axis and it's rotating about that axis, then whether it's a cylinder or a sphere or a disk, doesn't matter what shape it has, and whether it's spinning fast or spinning slow doesn't matter. It's always going to have the same gyromagnetic ratio. It's always going to have the same ratio of angular momentum to magnetic moment, but the electron's ratio is different by a factor of about 2, and that suggests maybe it's not actually a spinning body. Right? If it was a spinning body, you'd expect a certain gyromagnetic ratio, you get a different one. Okay, what could be going on? Well, when you look at what's going on in the Dirac field, you can define a velocity of energy flow, you can define a velocity of charge flow, and they don't always agree. And in fact, in simple cases, this factor of 2 in the gyromagnetic ratio comes from the fact that the charge is rotating faster than the mass. The charge is rotating twice as fast as the mass. So it's true that for a classical spinning body, if the charge and the mass rotate together, it has a certain gyromagnetic ratio. But if the charge is rotating faster than the mass, it would have a different gyromagnetic ratio. And that seems to be what's happening for the electron. Okay. Now, to set up the second problem for a spinning electron, I want to bring out a little demonstration. So for this one here, we have a Hoberman sphere, big sphere, and we can set it rotating. If we set it rotating, it has a certain angular momentum, and that angular momentum stays approximately the same as it rotates. It rotates at a constant velocity. And you can think to yourself, what's going to happen if we make the sphere smaller while it's rotating? If it's rotating and we make the sphere smaller, is it going to spin at the same rate? Is it going to slow down? Is it going to speed up? We can see what happens. We can set it spinning. We can make it smaller, and it speeds up, right? Spins a lot faster. Doing it again. It's rotating, slow. Turn it, make it smaller, and it rotates a lot faster. Okay, so that property then sets up a problem for us for the idea that the electron spins. The electron's really small. We know what its angular momentum is. So if it's spinning, it better be spinning super fast. And there's a worry that the electron is so small that for it to be truly spinning, it would have to be spinning faster than the speed of light. And nothing can move faster than the speed of light. That's impossible. So it can't really be spinning. And the textbook that I mentioned with this idea that the electron's a structureless point particle includes this argument against the idea that the electron is really spinning. If it was spinning, it would have to spin faster than the speed of light. There's a little video version of the demonstration you just saw here. Another famous demonstration of this that's often used in physics text rooms is the example of spinning around on a chair. If you're spinning around on a chair and you're holding weights far out, when you bring those weights in, you spin faster. So as this mass gets closer to the axis of rotation, when the angular momentum stays the same, the body must spin faster. Okay. We can also make a version of this argument focusing on magnetic moment. We know how strong of a magnet the electron is. If that strength of magnet is the result of rotation of charge, the smaller the electron is, the faster that charge has to rotate. So that can also lead to a problem that we seem to need faster than light rotation. These problems arise if the electron is smaller than the Compton radius, h bar over mc, smaller than a certain size. And if you think the electron is a structureless point particle or something like it, if you think the electron is really tiny, some little dot moving around the nucleus of an atom, then I can see why you'd have this worry. But on the second option here, on this option where classically the electron is a lump in the Dirac field, is a kind of cloud in the Dirac field, and then in quantum mechanics, in quantum physics, we let that enter superpositions. The energy and charge are not that compactly centered, at least not usually. So in ordinary circumstances, the electron's energy and charge are spread out pretty widely, larger than the Compton radius. So that gives at least a partial response to this worry. Getting a full response to this worry is a bit more complicated. And there are some open questions here. But I think there's a quick answer here that on this picture, the electron is not that small, and so it doesn't have to rotate that fast to have its usual angular momentum and magnetic moment. Okay. So we've been asking these questions about what is an electron and how to understand electron spin, but we're actually getting at bigger issues here. We're getting at issues about how to understand all of these subatomic particles, all these pieces of the standard model. Electrons, photons, gluons, quarks, what are all these things? Is this particle physics, and these are a bunch of different quantum particles fundamentally? Or is this fundamentally quantum field theory? And each of these has a field associated with it. We should think of the fields as more fundamental than the particles. I argue for fields. I like the field approach better. So the kind of arguments that are being made here for the electron can be generalized. So when you approach quantum field theory, which is the theory in which the standard model is formulated, the theory that gets used in these particle colliders, the theory that is a combination of quantum mechanics and special relativity, that is are sort of like more advanced, better theory than ordinary quantum mechanics. What's this theory really about? What's the ontology? How should we understand the states in quantum field theory? There are two options here, two competing options. First, our states are kind of like the states we're used to from regular quantum mechanics. The states are particle wave functions. So the states take as input locations for point particles and return as output complex numbers. In ordinary quantum mechanics, the number of particles is usually fixed. We're talking about a single particle or we're talking about 5 particles, but the number of particles doesn't change and you can't get superpositions of different numbers of particles. In quantum field theory, we relax some of that. We say, okay, you can have superpositions of different numbers of particles in different arrangements. You can have particle creation and particle annihilation, but you could try to fundamentally hang on to the idea that the theory is about particle wave functions and their evolution. But there's an alternative picture of what's at the bottom in quantum field theory. It's not a theory of particle wave functions, it's a theory of field wave functionals. Kind of complicated term. A field wave functional takes as input a specification of what a classical field is doing everywhere. This picture is just a scalar field. Maybe you have a specification of what the electromagnetic field is doing everywhere, maybe a specification of what the Dirac field is doing everywhere, and outputs maybe a complex number. So these describe superpositions of things that fields might be doing. You get a very different picture of what the theory is fundamentally about. Okay. The debate between a particle approach to quantum field theory, where what you have is particle wave functions, and a field approach to quantum field theory, where what you have is field wave functionals, is to me a super interesting debate. It's a really hard debate. Making either of these options really work for all of quantum field theory is difficult. You can't just take the book off the shelf and say, yeah, I want to understand it all in terms of wave functionals, and it's easy. It's hard. Each of these approaches faces different challenges. I'm very interested in the debate between them. But I do want to flag, I like the second option better, but I don't think the coast is clear for that option. I don't think it's the obvious winner done and dusted. I think there's work to be done making it work. Okay. Now, you might have noticed that if you've encountered the philosophy of physics and questions about quantum physics before, that I haven't been talking about different interpretations of quantum mechanics in the talk tonight. So if you've heard about Bohmian mechanics, the many worlds interpretation, spontaneous collapse theories, this kind of thing, I didn't talk about it. I'm super interested in these ideas. I teach a class on this. It's important to me. But the debate between how quantum field theory should be formulated as a particle theory or a field theory with particle wave functions or field wave functionals, and how electron spin should be understood, largely cross-cuts the debate about different interpretations of quantum mechanics. You can take a many worlds interpretation where you think fields are more fundamental than particle, or a many worlds interpretation where you think the particles are more fundamental than fields. Same with Bohmian mechanics. There's sort of field-based Bohmian approaches. There's particle-based Bohmian approaches. So really interesting to combine these things. But I just want to flag that that's to some degree a separate debate. Okay. So the last thing I want to talk about is what's really going on inside atoms. There's an old picture of what's going on inside atoms, that the positive charge is spread diffusely throughout the atom, and the electrons are these little dots, these little raisins, what get called plums, inside the pudding of the positive charge, the plum pudding model of the atom. We don't believe that anymore. That's not the current picture of the atom. We don't think we have spread out positive charge with these little dots of negative charge in it. Another model you might have is what we could call a pure plum model of the atom. We've got point electrons going around a concentrated nucleus. It's not common to think of that as a correct model of the atom classically, where you just have these point particles going around. But I do think it's common in a quantum interpretation to think what we have is a bunch of quantum particles together in our atom, including quantum electrons that don't really spin and that are, in some sense, point particles. There's a third option, the option that I prefer, which you might call the inverse plum pudding model. We have spread out negative charge, the electrons. It's not just spread out because there's some probability density or something like that. Like each electron is spread out, the charge is spread out, the energy is spread out. Electrons are fundamentally larger things than you might have thought. They're not these little dots. And the nucleus is there in the middle. So these debates about what's going on in quantum field theory, they have real consequences for understanding physical systems and what's actually going on inside those physical systems. All right. So where does this leave us? Where are we now? We have equations that work well. I don't deny that. But what I want to emphasize here in this talk is that we know a lot less than you might have thought. You might have thought, look, science, physics has given us very precise theories of what's going on inside atoms. We have this very successful theory of quantum physics, and we have quantum field theory. Surely we know these things. Maybe you don't feel like you yourself understand, but you feel like humanity has figured this out. But I would say no. I think there's still a lot of open debate about what's really going on inside atoms. And I think it's kind of exciting to realize that, to say, wow, we have good equations here, but we don't know what exactly is going on. And there's room to debate it. So experts disagree about the structure of the atom. They disagree about whether electrons truly spin. These questions are hard to settle, but I do think there's ways to make progress. And I hope you've gotten a bit of a glimpse of how you might make progress on these kind of questions. It's not merely sort of philosophical armchair reflection that's not going to get you anywhere. There are ways to try to figure it out. All right. And so I leave you with the outline of the talk in case you might want to ask questions about different parts. Thank you so much.
We can take a couple of questions if you guys have. There's a question from the audience.
Hey, what interpretation of quantum mechanics do you favor and why?
That's a good question. So going back to this list of interpretations, well, I put on the list 3 of my favorites and 3 that are commonly favored among philosophers of physics, at least philosophers of physics who are drawn to what gets called a realist, or you might think of as a more concrete kind of laws and ontology based picture of what's going on in nature. So I do like these 3. Among these, I prefer Bohmian mechanics and many worlds interpretation. And I've also done work myself on a kind of hybrid theory that somewhere has some elements of many worlds and some elements of Bohmian mechanics. That's called sometimes called a many interacting worlds approach, which I quite like. But yeah, those are my favorites. I guess the short answer, yeah.
Additional question.
In the double slit experiment, if I recall correctly, the interference pattern collapses if there's a detector placed before the double slit, which detects the photon or the electron traveling before it reaches the double slit. But I would like to know how a detector detects a photon or electron going across its path at a 90-degree angle. I've never quite understood how you have a detector before the screen, which—
So like how could
screen,
you
the
have a
slit.
detector without catching it and stopping it? That's your question?
Something like that,
Yeah, good. Yeah, there's a nice, if you're interested in these issues, there's a nice book that I use as a textbook for my course on philosophy of quantum mechanics by Tim Maudlin called Philosophy of Physics, Quantum Theory. And in that textbook, he tries to demystify this idea of like observing which slit the particle goes through and that changing whether there's an interference pattern or not. So he introduces what he calls a micro observer. Instead of like thinking of a human checking which slit the particle goes through, he says you could just imagine that you're putting a negatively charged particle through the 2 slits. So maybe you're doing this experiment with electrons and you put a little proton in the middle. And with some idealizations, you could imagine that the electric attraction between the electron and the proton causes the proton to move towards whichever slit the electron went through. Now, maybe if the slits were long enough and the distances were right, you could imagine something like that potentially working out so that the proton kind of keeps a record of which slit the electron went through. The proton is displaced towards whichever slit the electron went to. I mean, it turns out that's enough to destroy the interference pattern. You don't need a human looking at it. You don't need a big thing. If all you're wondering is, does the interference pattern go away? Do the stripes go away? The stripes will go away if you have an additional single quantum particle that is keeping a record of which slit the electron goes through. Does that answer your question? Yeah. Okay.
Additional questions.
Hello. I have a question for the reverse plum.
Which one?
The reverse plum.
Oh, yeah.
So my question for this becomes, you know, in the pure plum, right? We have like electrons, right? And we know like atoms can give and take electrons, right?
Yeah.
How would we do something like that in the inverse plum pudding?
Good. So the electrons, they do seem more like mushed on top of each other or something like that if they're each these spread out kind of entities. So there are good questions there. I guess there are deeper things we could get into here, and there are some things that I'm still a bit puzzled about myself. But maybe the quickest answer is if two atoms exchange electrons for each other, they are losing some of their cloud, but not all of their cloud.
That makes sense, actually.
Yeah,
Thank
so you
you.
can imagine the cloud losing pieces of it breaking off. Yeah.
Okay, thank you.
Here we have.
Hi, really great presentation. I was curious, some of what you were talking about, especially with the nature of the electron, I'm kind of wondering what very high temperatures or very small, I guess, space-time structures inform us about the nature of the electron. For example, I guess just based on my thinking, I'm thinking like, when the Big Bang occurred, everything was in a very, very small infinitesimal point. And so you had extremely high temperatures and you had very small space-time. And now everything's spread out. So I was just curious, what does the nature of electron spin or just the electron in general, what do those really extremely high temperatures tell us about the nature of it potentially? And then also when I guess the Big Bang occurred and everything was very, very small, does that tell us anything about, perhaps the nature of the electron in those different states?
Yeah, I think it does. I have to think about this more for the early universe. I haven't thought of it so much particularly there, but sort of in general in quantum physics, when you have a body confined to a very small region, then it ends up having very high energy. It's got components with different high momenta. And so for the electron too, if you try to confine it to a very small region, it can be in states like that. It doesn't have to be spread out widely. I said before that it's sort of typically spread out more than the Compton radius, but it can be put into compact states. There are possible states for the electron that are more compact, but in those more compact states, it has a lot of energy. And by mass energy equivalence, it has a lot of mass. And when I was saying before that angular momentum, if something is smaller, it has to spin faster. And that's true if you keep the mass the same. But if you make it heavier, it actually doesn't have to spin that much faster. So I think what's going on with those compact electron states, my current understanding of what's going on there, is that in those states, there's actually a lot more energy, a lot more mass. And so it doesn't have to rotate faster than the speed of light in order to generate the regular angular momentum. It can still have its usual angular momentum. There's just more mass there to rotate when it's in those small states. But there's still more to figure out there. Yeah.
Okay, I see a couple more questions, but we'll save them for the Q&A panel. Let's thank our speaker. And so now is the part of the night, the choose your own adventure part. We're going to have the Q&A panel so you can ask questions related to the presentation, related to the philosophy of physics and science, or just related to astronomy and space science. We can answer those questions as well. We'll do that for the next hour or so. And we have telescopes. If you go out the front doors and follow the signs to the athletic field just behind us, it's about a 2-minute walk. There's 4 telescopes set up out there, and you're free to go back and forth between the 2 until about 10 o'clock. And we'll see you guys maybe at Astronomy on Tap or our next one of these in a month's time. Okay, we'll move forward in about 5 minutes. All right. Thank you guys for sticking around for our Q&A panel. What we'll do is we'll each go through and give a brief introduction to who we are and what sort of stuff we work on. We have a pretty unique panel tonight, consistent with the content of the presentation, of philosophers of science. And while they do have training in science, their focus is more on the philosophy, much like we heard about throughout the presentation. So we'll be better able to handle questions of that nature, but we can also handle questions on physics and astronomy, and we'll just do whatever we can do. So feel free to throw out questions as you may have them. One moment though. So as an introduction, I'm Cameron Hummels. I'm a research scientist here in astronomy. I know very little about philosophy, so I'm glad that you guys are taking up that side of the panel. My research is primarily related to galaxies, like our own Milky Way galaxy, and their distribution throughout the universe and their evolution over very long timescales. I primarily study that using computer simulations, so big supercomputer models of how galaxies form and then change over their lives, but their lives are a lot longer than ours. They typically live for billions of years as opposed to decades, or I guess centuries if you're really lucky as a human. So yeah, I can, but I do a lot of this so I can handle questions on whatever, but anyway.
Great. I'm Mahmoud Jallo. I'm a postdoc here. It's my coming on 1 year at Caltech in the history and philosophy of science. I'm working at the Einstein Papers Project, where we're publishing the collected works of Albert Einstein. We're currently on volume 18, which should be done soon. And actually, that volume covers the years 1930 to 1932, when he was visiting Caltech, in fact. So I've been thinking a lot about his interactions with Caltech legends like Hale and Millikan and so on.
Hi everyone, I'm Shelley Xu. I recently joined Caltech as a postdoc in philosophy of science. My research mainly has two parts. The first part focuses on philosophy of physics, especially philosophical and metaphysical questions with regard to the metaphysics of space-time in the context of general relativity. So I work on topics including Mach's principle, energy conservation in general relativity, and approximation methods in general relativity. And the second part of my research concerns the history of 20th century physics. I am right now working on a book project about the intellectual life of C.S. Wu, who was a Chinese-American physicist who did the 1957 parity violation experiment, and I'm trying to situate her life within the broader context of Chinese scientific diaspora of the 20th century, and looking at how Cold War politics and how immigration policies shape scientists' career trajectories and the process of knowledge production. Thank you.
I'm Chip Sebens. I just gave the talk, so you know about me a bit already. I've done this work on electron spin. I've done work on whether quantum field theory should be understood as a theory of fields or particles. I've done work on probability in the many worlds interpretation of quantum mechanics, work on the arrow of radiation in electromagnetism, has to do with the arrow of time, work on locality in quantum mechanics. I teach a course on philosophy through science fiction, lots of things we can talk about.
Oh, very interesting. Okay, so questions from the in-person audience. We also have we're live streaming on YouTube. I'll check if they have questions as well. I actually have a bunch of questions for you guys too. So if we don't have more questions, I'm happy to send it out.
Hi, I guess this question is mainly for Chip, but the other audience members, the other panelists can also answer it. You know, we talk about the philosophy of science and we talk about quantum mechanics and classical physics. We don't talk about the psychology, like the human brain wants to follow classical mechanics because it makes more sense as far as how we interpret rationality versus quantum mechanics, which can be counterintuitive, just the way our brain is structured. And how can you explain something to a person that doesn't have training in quantum mechanics about some of the principles you were talking about tonight and try to have them understand it better.
Yeah, excellent. Oh, yeah, give it a switch.
I'm very sympathetic to that kind of question because I feel like as you're learning quantum physics in the physics classroom, you're often told to let go of your classical intuitions to learn to think quantum mechanically. And I found that quite frustrating because I thought, yeah, sure, I can think quantum mechanically, but I need a clear story of what's going on. It doesn't have to be the classical story, but it has to be something. So the way I frame the talk today, where I think a careful statement of a physical theory should give clearly specified laws of ontology, that's what I think you need. And those don't have to be classical laws and they don't have to be a classical ontology, but it needs to be something. And I think that the various interpretations of quantum mechanics, all the ones that I like best, all do that. They give you at least some proposal as to what there is and what rules that stuff follows. To get more of an intuition about what's going on in quantum mechanics, I could tell you all about those different interpretations, but it would take a long time. So I think maybe as different questions come up, I can try to say more about that, but sort of getting into how each interpretation of quantum mechanics explains each weird aspect of quantum mechanics is a very long story, but I think an important one. I don't know if anyone else wanted to add anything.
Yeah, maybe it helps to consider the case of Einstein. I mean, I think he's one of the founders of quantum mechanics and a longtime critic. But I don't think it's right to say, which sometimes people say, but wrongly, that he didn't understand quantum mechanics or he couldn't adapt to quantum mechanics. He just had different standards for what a theory should look like. And I think similar to Chip, he has certain standards for what a good explanation is or looks like, or what it means to really understand a theory beyond just plugging and chugging and getting predictions out of it.
That's interesting. I just want to kind of take off on that and kind of start a discussion because probably I have a lot of questions and maybe you guys can help answer them. Classical physics, that is, moving bodies or even electromagnetism, we have some intuition because certainly for moving bodies, this is something we've experienced for our entire lives. But quantum mechanics is describing things on subatomic scales or very small scales that we don't have a lot of intuition. And I wonder if we were able to perceive things in our everyday experience, like the fuzziness of the electron cloud or something like that, if it would make more sense to us other than, writing down equations and seeing those equations and seeing the outcomes of different experiments, but gaining some actual intuition and having it make sense for us. I don't know, maybe it's just one of experience that we don't encounter those kind of conditions in the same way that relativity is also a little bit counterintuitive because we don't typically travel near the speed of light or get very close to supermassive objects where time dilation is a factor, that sort of thing. So I wonder, is it just, and are there other corners of modern physics that touch on areas that we don't have as much intuition for simply because they're outside the experience of most humans? I don't know. Presumably?
Yeah, I think that there's a couple of things to say there. So first, I think the comparison with special relativity is interesting because with special relativity, it is unintuitive. It's kind of surprising that you can't just keep pushing something and accelerate it faster than the speed of light. Why not? Can't I just make it go faster and faster?
Just keep push, yeah. Exactly.
Yeah, can't I just keep pushing? So there's a lot of things that are unintuitive there. But from a philosophical standpoint, many of those, they're not really problems with the laws of ontology. Like it's telling you a clear picture of what's happening in nature. It's unintuitive, it's not familiar, it's not what we're used to, but it's clear enough, largely. Quantum mechanics is not like that. It's not that quantum mechanics is giving us some unintuitive picture of nature, but still a picture. It's barely giving us a picture, or it's hard to get a picture out of it. So I think there's work to be done to get a picture out of it. And then I think the candidate pictures that have been offered, the ideas about what's really going on, you do get better intuition for them the more you interact with things like that. And it's true that we're not like directly interacting with subatomic particles kind of at our familiar scale, but many of these interpretations of quantum mechanics do offer you a way of visualizing that. And if you watch more of those videos, if you play with the equations, if you see how different states evolve, you do start to get more of an intuition for it. So I think that intuition is attainable, but I think the intuition is easiest to obtain when you have some kind of picture or some kind of ontology.
So related to that, as you say, our picture of quantum mechanics is kind of muddled. It's hard to put together a cohesive picture. And I wonder, is that just because our understanding of quantum mechanics is in its infancy, and there will be some breakthrough moment in a decade or 50 years or 100 years that will really clarify things and make it a much more clear picture that we currently lack? Or is it just intrinsically a messy business that we're never really going to have a clear description of? And I don't have a good answer for that question.
I can keep speaking if it's
Sorry,
direct
I'm
to me.
sorry. This doesn't have to be.
No, it's okay.
I'm just curious.
But
about
maybe
this,
just quickly, I think, yeah, I'm hoping for that. That's why I'm doing this kind of work. And I think with more people doing it and more energy put into it, we're more likely to get that kind of breakthrough. So I would like to see that. I do think there's a decent chance that the breakthroughs already happen, in the sense that there exist various clear pictures of what's going on in quantum mechanics. It is hard to settle which of them is right, but they are out there. So people have had these insights in the past and have come up with pretty good ideas as to what might be going on in quantum mechanics. It's just at the moment hard to settle which one is right. But I do think there's room for more. It's not obvious to me that we have laid out all the most promising interpretations of quantum mechanics or options for what's going on there.
Okay. Sorry, I don't mean to monopolize all the questions. When we have this wonderful question from this young man in the front row, it's going to blow all of our minds.
If a white hole is the opposite of a black hole, and a black hole looks like this, would a white hole be the opposite? Like this?
Yes. That's right. Oh, you've got more.
The opposite.
Oh, I see. Okay.
And if yes, could the black hole be connected to through the universe like this?
You have a lot of graphical. Yes, a wormhole. That's the question. So the question, if I may interpret this question more globally, we believe that black holes exist. There's plenty of pieces of evidence for black holes. If white holes also exist, could they be connected by some sort of space-time structure that allows the material to pass from the black hole to the white hole and then expel it out in the universe? Is that roughly what you're asking? That's a great question. It's a very advanced question. Do you guys want to handle it or should I? Please, Shelley, go ahead. We can do it collaboratively.
I also don't have a good answer to that question, but one interesting, so what you are drawing is actually a very beautiful diagram that people sometimes refer to it as a Penrose diagram. If you try to draw it at the 45 angle. So that was very beautiful, John. Yeah, so if we assume, for instance, time reversal invariance and general relativity, which people usually do because we don't seem to have other reasons to think that general relativity is special in a sense that it breaks the time reversal invariance, then you can have, for instance, extend your Schwarzschild black hole and back, and you would have a white hole. But can it actually exist? No one, I don't know. I don't have a very good answer to
I
that.
think you're right. I think you can have these things exist according to the Einstein field equations and according to most of the rules of physics, but there doesn't seem to be any actual evidence for them. Because whereas a black hole is challenging to see because stuff goes into it and light can't escape from its gravitational field, in a white hole, in the reverse, you have this stuff expelling all manner of mass or energy or radiation. And so the fact that it's white, it should be glowing. It should be quite bright, right? And you'd think that that thing would be pretty obvious. If it were right in front of us, we'd be able to see it. Or if it were in our solar system, or even in our galaxy, potentially we'd be able to see it. And we don't yet see any kind of evidence for this sort of object. So it may exist. White dwarfs exist. White holes may exist, but I don't think there's any clear evidence that they do. But yes, as you propose, one could have a white hole that was connected to a black hole through a space-time structure, like a wormhole that connects those and kind of funnels material between the two. And again, wormholes we do believe could exist. They obey the Einstein field equations, but they wouldn't happen naturally. They wouldn't just kind of spontaneously occur. There doesn't seem to be evidence for that. They'd have to be constructed. And we currently don't have the technology or the power to construct them. Maybe some other existing advanced civilization could do that, but we don't see evidence for it yet. But it could exist. We can't rule it out. So maybe. Does that answer your question well enough? Okay. Keep those good questions coming, though. These are always great. Okay, additional questions. Go with the gentleman here.
Hi, going back to the question of quantum mechanics and its interpretation and how intuitive it is. This past spring, I had to teach quantum mechanics to grade schoolers. And the first question I asked in my mind is, how do I do this? And one of the things I've been stewing about is we're taught from a very young age that something either behaves as a particle or something behaves as a wave. And then if you look at textbooks, it's taught from that point of view, it's one or the other. And then you get into your quantum mechanics courses and you learn that it's more complex than that. But it doesn't have to be that way. Shouldn't we be teaching it from it's both? It's not one or the other. It's just under what conditions are you observing that it's one or the other? And so what's your thoughts about changing the paradigm of how quantum mechanics is taught?
Yeah, that's a good question. I would like to change the paradigm of how it's taught. I think that these interpretations of quantum mechanics that have been developed, even though we are not certain which one of them is right, there are at least a handful that offer clear pictures as to what's going on in reality. And I think if you're taught those options, not taught one is definitively true, but taught a few things that might be going on, it helps you to get a grip on the theory. In particular, with this issue of wave-particle duality, it's often taught in a very mystical kind of way, where it's like, oh, it's kind of like a wave and kind of like a particle. What's really going on? Different interpretations are more clear, I think. They will either say it's really a wave that sometimes behaves or looks like a particle, or maybe it's really a particle, or in Bohmian mechanics, which I didn't talk about too much but mentioned in my talk, in Bohmian mechanics, you just have both. It's not that the particle is both a particle and a wave. It's that there is a particle and there is a wave, and the particle and wave interact with each other. And the wave kind of guides the particle or makes the particle move in a particular way. So in the double slit experiment, according to normal Bohmian mechanics, the particle actually goes through a particular slit, follows a definite path, always has a definite location. But you see an interference pattern because the particle is not all there is. There's also a wave. The wave goes through both slits. The wave interferes. The wave has this wavy behavior, follows the wave equation. And you see wave-particle duality because there's a wave and there's a particle. Bohmian mechanics might not be right, but Bohmian mechanics gives a very clear answer as to why there's wave-particle duality. So I would love it if quantum mechanics generally, your regular introductory course to quantum mechanics, whether taught in college or taught earlier as you're doing, expose students to some of these options as to what might really be going on, but that's not the current style.
Please.
Maybe a different approach would be also to look into the history more. I think, in a way, the wave-particle duality is very old. Newton had a particle theory of light. Huygens had a wave theory of light. When you look at sort of Huygens' approach to classical optics, right? He has a wave optics, but he starts off with thinking about light rays and then seeing, oh, well, how can I approximate light rays with waves? And so there's a way in which this problem's always been there from the beginning, right? And then with electromagnetism and Maxwell, you get the wave picture coming back again with kind of full strength. But this has always been a puzzle with light and how light interacts with matter. And so in a way, this problem is more fundamental than something tricky about quantum mechanics and its formalism or something like that. It's a very basic problem.
I'll just add a bit of historical aspect to that. When I was taught philosophy of quantum mechanics first, I was always motivated by this kind of narrative. Foundations of quantum mechanics were what Einstein and Schrödinger, all these great physicists were thinking about. But because of the Second World War, a lot of funding and resources kind of just go into building a bomb. So kind of foundational question in physics, and especially these questions that philosophers now pursue, are no longer viewed as kind of valuable in physics development. So there's kind of historical and sociological questions with regard to, in the background, when we teach quantum mechanics, we usually go for this so-called Copenhagen, shut up and calculate kind of practical approach, instead of actually going through the different kinds of interpretations that have really nice and clear ontology. And it was kind of interesting when I was first learning this, and Tim Mullen, one of the philosopher of physics Jim mentioned during the talk, told us that we are carrying the torch of Einstein. So that's what we're doing. We're trying to figure out these questions that were thought in the 40s, before, 30s and 40s. And these are interesting questions. It's just that because physics as a paradigm changed, because various reasons, including funding, these problems are no longer viewed as valuable within the physics department, or you can argue what is a valuable project, but I think there's also that reason why these kind of these interpretations are not actually taught or are popular within the physics.
So was there ever a point in the development of science in general, or physics specifically, where the philosophy of these and different interpretations, whether it's quantum mechanics or other, as you were referring to like Newton's day and Huygens and such, where the philosophy went alongside the actual physics? Whereas today, as you point out, much more of the focus is on practical matters, functionality of the physics, as opposed to what it actually means about the nature of reality. Like, was there a time when it was more, please?
Sure. Our best example is always Einstein. He was talking to philosophers, and he was also deeply influenced by Mach, Ernest Mach, David Hume. And he was also talking to a logician, Gödel, who came up with the Gödel universe. So Einstein was really pretty much motivated by this Machian picture, the relations view of space-time, when he was thinking about generalize his special theory of relativity to gravitational theory. And he was talking to philosophers about it. And if we look at, for instance, correspondence between de Sitter and Einstein in between 1916 and 1918, they were talking about philosophy, in particular Mach's principle, and whether we should explain inertia through matter, or inertia is something that is just can be left unexplained. So de Sitter thinks, well, inertia can be left unexplained, but Einstein thought that that was not satisfactory. We have to explain inertia through matter. And there are a lot of other examples in philosophy as well. I would also like to point out that if we look at, for instance, EPR paper, it was done in a very philosophical style. It would be, and if we look at
What's the EPR?
Einstein,
Podolsky-Rosen.
yeah, entanglement paper. It was probably one of the most cited paper of Einstein. It was very philosophically written. They have like clearly articulated premises. And even in the 60s, when people write theories about modified gravity, for instance, Brandstke theory, they start their physical review letter with like Leibniz and Huygens. And if you start your paper nowadays with that kind of approach, it would be rejected.
Ignored.
Yeah, so as a historian and philosopher, it was kind of fun to read these papers in the past, because these physicists are not really scared of, articulating their philosophical views, and they're really expressive. And it's kind of interesting to see how that changed.
Over decades.
Yeah.
Let me just pick up the thread with the so-called EPR paper. So in 1935, Einstein, Podolsky, and Rosen published a paper called Is Quantum Mechanics Complete? And that launched, well, Einstein had some quibbles with how things got put in the paper, because Rosen wrote it because he knew English. But setting that aside, that put forward a version of Einstein's classic critique of quantum mechanics, which is that something about quantum mechanics is not just weird or unintuitive, but actually it's giving us a theory that's incomplete. There's some information about the world. There's some properties about these bodies that somehow aren't getting into the quantum description, and that's the cause of all these paradoxes. Now, there was actually a very lively debate from that paper, but the issue kind of fell by the wayside a little bit, except for the fact that that paper, presents a very good model for thinking about entanglement. So the essential structure, so you have two particles together that sort of have some conserved quantity, maybe spin, maybe polarization or something. You send them very far apart. You look at one, well, then the other one seems to have the opposite property. And so there's a few different options for interpreting that, but all of them seem wrong. Either you have action at a distance, or there's some hidden variable that isn't in quantum mechanics, but was somehow there. And there are various no-go theorems about that. But in any case, that kind of fell as a philosophical problem, or a fundamental problem, it kind of laid silent for some decades until John Bell in the 60s, a physicist at CERN, was kind of moonlighting as a quantum foundationalist or a philosopher of physics. And he started to think more about if we could tell whether or not quantum mechanics is complete or incomplete. And he came up with these famous Bell inequalities that then later, through some philosophers like Abner Shimoni, who called it experimental metaphysics, came up with ways of actually testing these inequalities. And that ended up, those results are foundational to quantum computing and ended up getting the Nobel Prize for Physics in, when was that, 2017? Yeah. Alan Aspect and all of them that got that Nobel Prize. So that's a case again where this kind of foundational philosophical problem led both to practical results like quantum computing and thinking about entanglement as like a fundamental property or fundamental aspect of quantum mechanics, and then also recognition in the physics community in the highest form of the Nobel Prize. So I think there are good cases.
Yeah, no, that's awesome. That's great. Okay, lots more questions. Get this gentleman over here.
I might actually just add an example for the synthesis of physics and philosophy. Newton's three laws, if you look at the development of those, is by and large basically doing philosophy of physics style critiques of Descartes' conception of motion. So I'd add that in, but I actually had a question for Chip about his talk. I found myself really liking that I could get a picture of the electron spinning of this field configuration with some rotational quality. But then I started to wonder, well, where do I find orbital angular momentum now? If orbital angular momentum was supposed to be the quality of the electron field spinning, is there room for it still? How do you fit both together? Can you give a unified picture of the two? And just how worked out is that picture?
Chip?
Okay, that's a great question. My understanding of what's going on there is that in this kind of picture, orbital angular momentum and spin angular momentum are not as different as you might have thought. It all has to do with the flow of energy and charge in the Dirac field. It's true that I focused today on spin angular momentum and didn't say anything about orbital angular momentum, but you can look at the current density of the Dirac field, and you can look at the momentum density or energy flux density of the Dirac field. These are going to be like two different flows, and each of these can be divided into components. You can sort of break them down, expand them in certain ways, and there's one piece that you can identify as the spin piece. You can say, okay, I see this piece of the current density is the current density associated with spin, and this part of the momentum density is the part associated with spin. But there's more, not just that part. And the other pieces of the current density and the momentum density can also give rise to rotational motion around a central axis. And it's my understanding that those pieces would give rise to orbital angular momentum. So in the math, you can separate them. There are like different terms that are responsible for orbital angular momentum and spin angular momentum. But like physically, what's happening in each case, there's a flow of energy and charge in the Dirac field. It's one field. I would say it's one field. It's got a particular, it's got densities of energy and densities of charge, and it's got flows of energy and flows of charge. And those flows of energy and charge mathematically can be separated into these different pieces, these different contributions, some of which are associated with angular momentum or with orbital or spin angular momentum. But I mean, to some degree, it's a sort of mathematical decomposition. What's happening physically is a single flow that is the sum or combination of those different effects, as I understand it. Yeah.
Okay, before we get to additional questions, I should just mention that the telescopes are only running for another 10 minutes or so. So if you haven't had the opportunity to look through the telescopes and you want to, now is the time to get out there and check out. We'll still be going for another 30 minutes or so, so feel free to check them out and we'll still be going. But I just don't want people to miss out on the opportunity to look at some cool stuff in the sky. They are aimed at the first quarter moon, Hercules cluster, Ring Nebula, Dumbbell Nebula. So two planetary nebula that are really beautiful. One that looks like a beautiful rainbow Cheerio on the sky, the Ring Nebula. The dumbbell doesn't really look like a dumbbell. It looks more like a colorful hourglass. And then the Hercules cluster, which is a globular cluster of about 500,000 stars that are all orbiting the same reasonably dense structure. And so you have a bunch of stars that look pretty awesome. So, okay, continuing the questions for the panel.
Okay, I have a question that is about, if hopefully I formulate this correctly, the ontology of gravity. So your section on magnetic fields, as an astronomer, we talk a lot about gravity fields. And I asked myself, are gravity fields real? I think the answer is no, but I'm going to ask that in the context of a bigger question. There's a few ways that we have learned about gravity, right? One is as a field. A long time ago, there was this idea of like a particle that carried gravity between things. I think it was a graviton or something. And then of course, there's the gravity is just a change in the metric of space-time. So, and there's probably more that you can tell me about. Which of these, well, I think we know the third one is real, but how do we know? Like, what are the observations, like you talked about for the charged particles, that ruled out the other things? And please feel free to correct my question if I've already said something incorrect.
That's a very good question. It's a very big controversy amongst philosophers of physics, how to best think about the ontology of gravity and general relativity and all of that. I think the first approximation, and I'll say that, you know, the analogy between electricity and magnetism and gravity and general relativity is a very interesting one, and there's a lot of connections that Chip can tell you a lot about, sort of analogies between the two and how you construct things. Of course, given where we are, you know, the greatest connection, right, is that you have gravitational waves and you have electromagnetic waves. And I think as Chip put it, I mean, maybe he didn't put it exactly like this, but maybe one way to think about an argument for the reality of the electromagnetic field, which I think was why Hertz's discovery of electromagnetic waves was so important, was that if you have these waves of energy and it can actually affect things, then it means that the fields that those waves live in have to be real, or at least that's what you might think. Similarly, I think, you know, gravitational waves are one of the great confirmations of general relativity. It tells you that, oh, these things are really, you know, there is something actually rippling in space-time. And this idea of space-time curvature is not just some very abstract thing that maybe we can explain away because it only appears at very large distances, and we're going to try to explain away the eclipse data or something else. So I think the first approximation is to say, yeah, there is a field for gravitational phenomena, space-time, which is the thing that's so weird about, or unintuitive about, general relativity. Now, there are other ways to interpret this, but maybe Shelley or Chip want to say something about it.
Okay, so I think, yeah, I was saying before that, you know, one thing philosophers of physics do is, you know, look at these equations and think about different ways of interpreting them, different ideas about what they might mean or what they might be talking about. And with general relativity, we have the Einstein field equations, and they're normally thought of as equations describing space-time curvature and the way in which matter setting up the way in which matter is going to move through space-time. And we think of general relativity that way as a theory of space-time curvature. And then it sounds like gravity is not a field anymore. There's just space-time and things are moving in space-time, and space-time is just not as simple as you thought it was. But actually, when you look at the Einstein field equations, there's another way to interpret them. There's another way to sort of break them into pieces and analyze what's going on, where you think there's a background space-time that might be flat, or maybe it's not flat. You have a background space-time, and then you have a field on that space-time. And that's the gravitational field. And you can keep actually the same equation largely intact without changing it. You can say this equation works, I want to use it, but I'm going to break things down into a different way. So I'm going to take the metric and maybe separate it into a flat part and the everything but the flat part. And the everything but the flat part I'm going to view as a kind of field, or to be more precise, a potential that you get a field from. And this is sometimes called a classical spin 2 approach to general relativity. And I really like this idea. I find it quite intriguing, and I'm curious how far it can be pushed. It does seem like it's going to involve removing some solutions to general relativity. There are some things that are allowed on the gravity as curvature approach that won't be allowed as the gravity as field on flat spacetime approach. But it's not clear that you need to throw out the thing. It's not clear to me anyway that you need to throw out the things that are actually happening. So it might be, good enough to account for our world. So I find this very intriguing possibility that gravity, even though it's taught as a theory of curved spacetime, might be reinterpreted as a theory of a field on spacetime. And if you look at Feynman's book on general relativity and Weinberg's book on general relativity, they're kind of in this direction, kind of like particle physicists looking at general relativity, and the way in which they write about it and formulate it, they make it look more like the other field theories they're familiar with, and it sort of feels more like you have a gravitational field. Although in the end, they sort of go in the direction that Mahmoud was going in, saying, this is equivalent to the regular presentation, or I'm not saying anything different here. You can still understand gravity as curvature. But if you take them a little more seriously and you think, no, this could be a theory of gravity as a field on spacetime.
I think this is a very interesting, very historically rich and philosophically rich question. There are a lot we can say here, but I'll try to organize my thoughts into 3 parts. And the first one is, usually when we introduce field, historically, a lot of physicists are concerned about action at distance. So that was even at Newton's time, you have Poisson equation, but what is really, it has to be something in between. How can you have some kind of instantaneous effect, right? Even Newton, even though his equation seems to suggest that there is instantaneous gravitational effect, he was in fact concerned about this. And then we have a rich history in ether, and Poincaré and Lorentz and Einstein also talk about ether. And Einstein in 1920 Leiden lecture, when he was invited by Lorentz to give an inaugural lecture, he actually used Mach's ether to describe to refer to gravitational field. So there he was going through the history of action at distance, why physicists were concerned about it, and saying that gravitational field is Mach's ether. We have to have something between a field, between matter, in order for things to propagate. And in fact, we can kind of decompose our metric field, or so-called gravitational field, which is actually gravitational potential, but we can decompose that into the propagation part, which has 2 degrees of freedom, and that's why people call it spin 2. And that is kind of what we get, that is associated with gravitational waves. So we have propagating degrees of freedom, and gravitational effect does propagate at the speed of light. So in that sense, field must exist at least as a kind of medium. Now, the second point is that there is actually, again, a rich history about whether gravitational energy is real, related to the question whether gravitational field is real, because when we ask what is real, what do we mean by that, right? Do you mean that it exists on a par as matter? Is field as real as matter? And how do we define matter? And usually when we ask these questions, we kind of define matter or what is real through energy. So if gravitational field has energy, then we can say it's real. And it turns out it's very difficult to define gravitational energy because it's not local. You can have a kind of gravitational energy if you do approximation methods. And in fact, that's what we do in, for instance, Minkowski, in all kinds of gravitational wave calculations, we do a kind of split between the background and perturbation. So there you can have an approximate notion of energy, but you cannot localize gravitational energy of the field. And then there's also recent progress in quasi-local definition of gravitational energy. It's very complicated there, but there is a genuine question: what do we mean by real? And if we define it through energy, it seems that gravitational energy is not locally real, but at some scale, we can meaningfully talk about that it carries energy, so it is real. And finally, I think there's also a pedagogical question here, as Chip said, this kind of top-down approach to general relativity, where you start with a manifold, a kind of differential geometry approach, which is very beautiful, and you geometrize gravity. And in fact, most of textbooks do use that approach. And Weinberg actually in his textbook for general relativity didn't go through that. He said, oh, geometry is just a tool. We shouldn't, just because we use it as a tool, it doesn't mean it's real. So we shouldn't really think about it as a mathematical entity as real. So he kind of liked this background plus perturbation and spin 2 approach, which also connects to his QFT approach. So there's also a pedagogical question, which is a better way to teach general relativity. And yeah, I'll stop here. Sorry, it's long.
Good question. Yeah. Another question.
Yeah. So I've always been interested in the intersection of philosophy and physics. And since you were talking about Bohm, I was thinking of Bohm and Jiddu Krishnamurti's conversations. And then you were mentioning Einstein and various philosophers. I often think of that photograph of Einstein and Tagore. Are there books you guys, Chip, Shelley, and Mahmood, that you would recommend that explore that further? Discussions between philosophers and physicists.
On the Einstein-Tagore connection, that will be in the forthcoming volume of the Einstein collected papers. So if you want to see the circumstances around that, you can look there. I'm trying to think of a good more kind of. Well, there are some.
I mean, I'm not sure it's exactly what you're asking for, but one book I would recommend is a good general audience for a broad audience introduction to the problems in the philosophy of physics with quantum mechanics and what's really going on in quantum mechanics, including some of the history of how we got into this mess and what the different prominent physicists were thinking and how they were talking to each other. I recommend Adam Becker's book, What is Real? It's called What is Real? It's a very nice book and very accessible.
What is real?
It's called What is Real? And then I also mentioned in response to one of the other questions, Tim Maudlin's book, Philosophy of Physics, Quantum Theory. That one's a bit harder to read without background, but might be readable and goes a bit deeper. So maybe What is Real first, and then Tim Maudlin's book next. Also, for anyone who's interested, on my personal website, you know my name from the talk. If you go to my personal website, I have syllabi for the classes I teach. And they all often have a textbook, and then they also have recommended readings for the various different days with the topics listed. So those are my personal recommendations on a bunch of different topics. So if there's anything you want to follow up on, you can look at the syllabi from the classes I teach.
One other suggestion that comes to mind is a bit more academic, but I think it's a enjoyable read. Mara Beller has an old book now called Quantum Dialogue about sort of debates at the foundations of quantum mechanics between the founders and sort of the rise of the Copenhagen interpretation. So at least particularly for quantum mechanics, that would be one that's sort of philosophically informed and motivated and following some of the debates between Bohr and Einstein and others. Mara Beller, Marabeller. It's maybe from the 80s.
And for those interested, I'll look up these different books and put them in the YouTube description along with links in case people want to find it afterwards. I'll try to for our record video audience. Additional questions in the last few minutes. Did you have a question? Or, oh, you have, okay.
This is a controversial one, but I asked Sean Carroll this same question, and then a few months later, he decided to switch to Johns Hopkins. So, you know, this is the end of the night. What is it like to research and teach the intersection of philosophy and physics in a school whose motto is shut up and calculate?
I don't know if I'd say the motto is shut up and calculate always, but you know, that can be the attitude within physics. And I guess I've been saying a lot of things today that maybe make it sound like I'm pretty disparaging of what's happening in physics departments. But I do think a lot of the attitude is reasonable, and there's a case to be made for it. Many of these questions about the foundations of quantum mechanics have been around for 100 years or so, and it's been hard to make definitive progress on them. So there is a feeling among physicists sometimes with decent justification that you're not going to get anywhere working on these problems. People have been trying for a long time and they haven't gotten anywhere, so don't waste your time on it. And there's something to that. Philosophers are much more comfortable with problems that people haven't made progress on for a long time. We do a lot of unanswerable or hard to answer questions. Philosophers tend to pick the problems that are important, even if they're very hard to answer. And I think that's okay. So it's a different thing to be doing. And I'd hope that we can at some point break through and make more progress here. I think there has been progress in a certain way. But yeah, as far as teaching the students go, I think the students are very open to these things, and I have a great experience teaching the students at Caltech. I think they're wonderful, and I hope one of the impacts I can have teaching here is to take these students who might not otherwise be exposed to philosophical questions about physics and might just be getting a sort of straight physics curriculum, and showing them that there are these philosophical questions that can be asked, that they can be asked in a way that gets somewhere, makes some progress, find some answers, even if you don't answer everything. And I do often get feedback from students that it helps them to understand the physical theories better, that they have a better intuition, better grasp, better feel for it once they've seen some of these options as to what might really be going on, and they've dug into it in this way. So I think it's a kind of education that complements their straight physics education, teaching them to ask different kinds of questions, to understand the theories in a different way, and give them a lot of practice with writing and writing carefully and precisely. Philosophy has very high standards for precise writing. So those are a few things I can say. No.
Yeah, I mean, the astrophysicists have been friendly to me when I sit in on their classes, so it hasn't been too bad. I think, especially thinking about a project like the Einstein Papers project, I mean, this has to be like, one of the best places in the world it could possibly be hosted. There's so much opportunity, just the atmosphere, but also just opportunity to learn from the community and for interactions. Kip Thorne is on the board of the project and things like that. So, and there are events like this that happen on occasion. So maybe there can be more of that, but I do think there's the general, I guess, Caltech ethos, just being such a small school, there's such a lot of opportunity for collaboration. And so maybe we haven't fully followed through on that as we could, but I think it's there, and hopefully the barriers aren't too bad.
Related to that last part, so you talked about how you're helping oversee the Einstein Papers project.
I wouldn't say oversee.
Okay, you're involved in the Einstein Papers project. And we can learn a lot about Einstein's views, both philosophical as well as scientific, from his correspondence that he had over the many years of his life. But in the modern day, most of our correspondence is either verbally or through electronic means where that might not be saved. Do you think we are at a deficit in today if, future generations are trying to understand the fundamental work that Professor Sebens has done or that you've done or others in the field have done, that there won't be the same written record that we have of some of the historical scientists that we can do this with?
Yeah, that's bait because this is a subject I've been ranting about and having conversations
it?
with
Okay.
people a lot recently.
I wasn't a plant.
No, I'll try not to rant. Yeah, I think it's a problem. I think archivists are starting to think about it. I think actually the archive here has at least one recently deceased professor's email archive, and they're trying to figure out how to do things digitally and so on. I mean, there's maybe some precedents for this. So, at some point, telephones were invented and became common, and so we lost a lot of correspondence proportionally then. Already you have the case where, even Einstein, for example, if you're, a young postdoc or professor and you don't think of yourself as a bigwig, and maybe you aren't then, but you might be later, of course, we care almost, usually we care the most about the earliest things to kind of trace their development. But, usually you don't start saving your letters until you think you're somebody. So these are problems that have already occurred to some degree, but I do think this is a phase shift. I mean, there are extra problems we can add with, if people change universities, outside universities destroy the email accounts. I think also just email and other digital communication has kind of killed the genre of correspondence, right? Like, I have intellectual correspondence with people, but they're not like, reading Einstein and Bohr or Einstein and Aaron Fest corresponding in the 30s, right? So I think there's a lot of loss there. I think there are things we can do to fill the gap, and I think we're seeing a growth in the culture of doing oral histories, which also solves the problem of not asking people questions while they're still there to answer them. So I think there are some ways we can fill the gaps, but I do think there's going to be a particular kind of textual evidence that will be missing from the historical record, and what we do have will just be of a different kind than before.
We can take a couple remaining questions.
Hi. So I'm more interested in like the philosophy aspect because I didn't know that this was a topic that would be discussed at a school like this. So it's actually really fascinating to hear this. I remember, Chip, you said something like when you were starting, like you need a story, like you need something to sort of hook you into like what the natural order is. So I'm kind of wondering when you're teaching something like this, when you're teaching quantum mechanics or any aspect of science that might go against practical intuition, do you feel like for us, it's like we're trying to write the story of nature, or are we trying to read the book? Like, are we trying to interpret science as it's explaining itself to us, or are we interpreting it as we understand it?
Good. Yeah, philosophers of science are really interested in this kind of question. And the way it's often put, if I understand your question right, is the question of whether in science we are making discoveries or inventing models or something like that. Like, is the process of science a process of more like invention or more like discovery, or discovering the way the world really is? And so I think that the like inventing models kind of picture is more pessimistic in my mind. It's kind of like, well, yeah, we make a model that works, but who knows if that's what's actually happening in nature or not. And then like when that model breaks down, we come up with a better model, and it's this thing that we don't trust too much. You don't take your models too seriously because it's always just a model, and you're going to try to invent a better one. Whereas if you think you're discovering what's really going on in nature, then you think, oh yeah, you figured something out, and like we might figure out more, but we figured this out so far, and that's great. And it's not, you're not certain that it's right. It could be wrong, but we think we've made a real discovery here. So I tend to be like on the very optimistic side. I think we're figuring out what's happening in nature. We're not just discovering, we're not just inventing models that work. We're learning things about what's really going on in nature. And I think science can give us that. So with quantum mechanics in particular, I'm not just looking for a recipe book or a set of tools that makes accurate predictions, some kind of black box that you can plug and chug and get the predictions for what's going to happen in your experiments. I'm looking for possible pictures of what's actually going on in nature, and then hopefully to figure out which one is right. So yeah, I think I hope that we are making discoveries, and some things haven't been settled yet, but I think can be.
There's, I guess, another philosophical aspect of your question that might be related to this long and ongoing debate in philosophy of science there are different views of law. So when you said, are we trying to tell a story, in philosophers of science language, we always are concerned about what are like the laws of nature and what is the nature of the law. So there is usually, we say there are like two camps. There's the Humean, who think that we observe a lot of different data and then on the so-called Humean mosaic. So we have the world, we make local observations and we try to summarize the patterns, and laws in some sense are just a really simple and informative summary of what we observe. Now there's another view that is not Humean. It says that laws actually govern the particular. So laws are in a sense God-given, although this is a very biased way to put it because I am myself a Humean. So you can imagine laws are God-given, and so laws govern each particulars. So depending on which view you have, you can also say, oh, when we try to tell a story about the physics, are we using laws in such a way that we acknowledge that laws are customized to us? So in a sense, humans have human laws, and dogs will have a set of different rules how they approach the world, and we have our limitations as with regard to our access to the world. So there's also a philosophical debate with regard to the nature of laws.
Okay. Oh, there's still lots of questions. Oh my goodness. You have a question?
Okay, well, I hope you guys can help me because this question is half-baked and I'm thinking of a paper I read back in grad school years ago. There's a paper by James Weatherall where he talks about the theoretical equivalence of Newtonian gravity and geometrized Newtonian gravity. And let's see, where did it go? He thinks it's interesting because they're theoretically equivalent, but they describe a different geometry of space-time. And I don't remember fully the conclusion. I obviously don't remember the argument, but he is, I think, arguing against conventionalism, which he associates with Poincaré and other people. So I guess this question is a little open-ended. I'm just curious what thoughts you guys have on that general debate. And as a kind of tangential corollary, have there ever been any geometries of space-time, any non-Euclidean geometries of space-time that have been taken seriously in the history of physics?
So I don't have a view on conventionalists or non-conventionalist of space-time, but it's true that, yeah, Jim Weatherall has said a series of paper, I think, in Newton-Cartan theory, and then there's also, I think, what's it called? Teleparallel equivalence of gravity. So a lot of philosophers are working on that, and the later part of your question, could you repeat the later part of your question? Oh, non-Euclidean geometry. Of course, yeah. Sorry, I remember that and it slipped. Yeah, of course. Most people who took geog would usually take Riemann geometry as one of the classic examples. And there is still active debate in philosophy about conventionalism, but I myself don't have a strong opinion on that.
Yeah, maybe I can just say more for others that, I mean, we were earlier talking about different interpretations of general relativity, and this is maybe another axis in which you can think about different interpretations of general relativity. So one way to think about it is general relativity showed us that space-time has to be Riemannian and it has to be curved, at least in kind of a general sense. It can be flat on large scales depending on how the cosmology shakes out, but locally it can be curved, right? Well, not super locally either. But you can have the kind of picture that Chip was describing earlier. If you separate out the metric, you can say, well, actually space-time itself is flat. It's Lorentzian, but we have this extra field on it as the gravitational field, and it's not, the waves aren't in space-time itself, but they're in this field or whatever. There's another kind of class of equivalences that Weatherall, who's a professor at UC Irvine, and I've learned recently, especially the Oxford set of philosophers of physics will often call the Trinity. And so these are, so usually when you interpret gravity, general relativity as a theory of gravity, you say, well, what aspect of the...
No, it's...
Yeah, so I'll be quick. You can ask yourself, well, what part of the changes in the geometry, or how am I going to represent gravity geometrically? The usual way is as curvature. Another way is as torsion, which more or less says that things that are parallel don't stay parallel when they go far away. That's Einstein's teleparallel theory or version of GR from the 20s. And another way is non-metricality, which says something like, well, things can actually, if you like move a rod, not for like length contraction reasons, or I guess in a certain sense, in a generalized way, things might not stay the same size depending on where they are in the room or something like that. And those are three different ways to geometrically interpret gravity in a general relativistic framework or a Riemannian framework. Now, there are questions about how equivalent they really are, but the usual first pass is that these are three equivalent ways. And if you thought then that GR told you that spacetime is curved, well, that seems to not necessarily be the case. And that's a problem if you want to be a realist about general relativity, about the laws. If you want to say that this is actually telling us something about the world, well, it seems like we don't know what it's telling us about the world. Is it telling us that spacetime's curved, or that parallel lines don't go on forever, or what?
Okay, the room already told us that it's the end of the night by shutting off our microphones. I'm sorry. If there are still questions, feel free to come up. You can ask them, or if they are like, we're going to bed, you can ask me and I can try and answer. Thank you guys for your attention. Let's thank our speaker and our panelists. Great job. And I should just remind you guys, our next one of these will be September 18th, about some planetary object, probably Venus. And our next Astronomy on Tap is a week from Monday on telescopes. Hopefully we'll see you then. Have a great evening and weekend. Thank you.